Hello everyone, my name is Zhao Penghai, a PhD student from Nankai University. It's a great honor to share our work with you today. Let me begin by explaining the title. Our study focuses on predicting the impact of articles, and we approach this with large language models. Our conclusion is summed up in the phrase, from words to words, highlighting how words can transform into measurable scholarly impact.
So, what exactly is article impact prediction? It's quite similar to many other prediction tasks, like the well-known Boston housing price prediction. The idea is to take features related to a paper, such as early citation patterns, journal attributes, the reputation of the author's institutions, and so on. We feed them into models like decision trees, SVM, or neural networks to establish a mapping between these features and targets like citation counts. Traditional approaches have largely followed this pattern. Predicting paper impact is actually super useful. Big institutions could use this kind of tech to make smarter decisions about how to allocate resources. And AI systems might benefit too. For example, AI for science has been a hot topic lately. Consider the paper AI Scientist, published in August 2024. It describes an agent system that can handle the entire research process from generating ideas to writing papers, all fully automated. Impact prediction models could help systems like this sift through papers more effectively. Article impact prediction might also be helpful for you. For example, in the computer vision category on Arxiv, you'll see 100 to 200 papers posted every day, and on some days, nearly 300. No one can literally read through all of that. But with an impact prediction model, we could easily sort out the most valuable work, cut through the clutter, and make research way more efficient. Why didn't the earlier methods for article impact prediction attract significant attention? I think there might be three main reasons. First, in real-world scenarios, like browsing Archive, you won't find information like the author's affiliations or the journal where the paper was published. All you get is the author's names. Sure, sharp-eyed readers might notice something like accepted in ISBI added by the author, but since that's self-reported, its reliability is questionable. A more extreme example is double-blind peer review, where neither the authors nor the reviewers know each other's identities, and the reviewers can only assess the content of the paper itself. In such cases, traditional methods, which rely heavily on external input data, simply can't make accurate predictions. The second issue is that due to their heavy reliance on external data, most previous methods could only evaluate papers that were already indexed. Traditional methods often took advantage of additional information available for indexed papers, such as using journal impact factors to predict the influence of individual articles. Personally, I see two major issues with this approach. First, it risks data leakage. Second, it somewhat contradicts the principles outlined in the Leiden Manifesto, which discourages relying on journal metrics to assess individual research. Let me illustrate this with a bad ending story to show why using journal metrics for individual papers can be problematic. Back in the 1950s, there was a brilliant chemist named Boris Belousov. While studying energy metabolism in living organisms, he stumbled upon a chemical reaction, now called the BZ reaction, where the solution's color would periodically change. Naturally, he was thrilled and spent the next 8 years submitting his findings to top journals. But here's the twist. The chemistry community at the time firmly believed such a reaction was impossible, since it went against the accepted idea that chemical reactions could only proceed in one direction. Without even attempting to replicate his work, editors dismissed it as experimental error, and his papers were repeatedly rejected. After 8 years of constant rejection, Belousov gave up on academia in 1958 and left the field altogether. Tragically, he passed away over a decade later, unrecognized for his groundbreaking discovery. It wasn't until after his death, much like the story of Van Gogh, that the world realized the true value of his work. The BZ reaction turned out to be a cornerstone for fields like chaos theory and nonlinear dynamics. This tragedy had many causes, but one undeniable factor was the over-reliance on journal metrics to judge individual papers. Such a system risks stifling scientific progress and silencing groundbreaking discoveries. The final issue is that the prediction target itself is a matter of debate. This debate is quite easy to understand, especially when we use citation counts as an example. Citation practices vary significantly across different fields. For instance, TPAMI, one of the leading journals in AI, has an impact factor of around 20.8. Now, you might be wondering, what about Nature? Well, Nature boasts an impact factor of 50.5. But what's truly striking is the citation count for some of the top journals in oncology, which averages a staggering 521.6, over 20 times that of TPAMI. This discrepancy is not only found between broad fields, it also exists within the same field. Research on diffusion models or multimodal learning tends to attract far more attention than research on ancient document recognition. Even when the quality of research and its contribution to their respective fields are on par, citation counts can still differ by several times. This inherent imbalance in citation practices makes it incredibly difficult to standardize metrics across various fields or subfields. These challenges have significantly limited the performance of earlier methods and their effectiveness in real-world applications. So, how do we plan to address these issues? We're starting by addressing the most critical aspect, the prediction target. Our aim is to use a metric that applies to individual papers and allows for cross-disciplinary comparison. TNCSI fits this requirement perfectly. It's actually based on one of our previous studies, where we introduced a normalized metric designed for cross-field evaluation. The process works like this. We use the paper's title and abstract to guide the LLM in extracting key phrases. These key phrases are then used as search terms on Semantic Scholar to retrieve 1,000 related papers. From there, we model the citation distribution of these papers into a continuous probability density function. TNCSI is calculated as the integral of the PDF over a specific range, essentially representing the probability that the target paper's citation count exceeds those of other papers in the same field. Now, you might ask, can we predict TNCSI? Let's break down its pros and cons. First, TNCSI is highly interpretable. It's simply a probability. This means it's normalized, which is a big plus for neural networks. Unlike raw citation counts, which can range from 0 to tens of thousands, creating massive gradient fluctuations that hinder training, TNCSI avoids this issue entirely. Moreover, it accounts for differences between fields, making it possible to evaluate individual papers across disciplines. However, TNCSI was originally designed for reviews and cannot be directly applied to evaluate individual papers. Secondly, to align with the concept of citation counts, TNCSI exhibits a cumulative effect. In this work, we've addressed and improved two key limitations, or rather, inadequacies of TNCSI. The first issue is that TNCSI primarily focuses on review articles. To tackle this, we refined the prompts used to guide the LLM. The second improvement relates to cumulative impact. We constrained the retrieval range of related literature. While TNCSI searches without any time restriction, TNCSISP strictly limits the search to papers published within a 6-month window before and after the target paper. Let me give you a simple analogy to illustrate this. With the original TNCSI, it's like comparing the work of a first-year PhD student to that of a seasoned academician. The outcome is obvious. But TNCSISP only compares you to your peers, like your classmates. You just need to outperform others at the same career stage, which is much more reasonable. Once we've defined the training objective, we can move on to training the model. Overall, we followed the standard approach of fine-tuning large language models. We wrapped the title and abstract in the previously introduced prompt template. For training, we used LoRA, a method where the original model parameters remain frozen, and only a small additional adapter is trained. The model operates in an autoregressive mode, where the first generated token attends to all preceding tokens. In other words, this token captures the complete semantic context of the title, abstract, and prompt template. We pass this token through an MLP to predict the TNCSP value. Since TNCSP is a normalized metric, we applied a sigmoid function to clamp the output strictly between 0 and 1. Our experiments were conducted on A40 GPUs, and when scaled to more common hardware, like a single 3090, the total training time would be less than a day. This computational requirement is reasonable for most universities or institutions. In our evaluations, Llama 3 outperformed other models, achieving an error of just 0.216 on this 0 to 1 prediction task. Moreover, its NDCG score, a measure of the model's ability to identify highly influential papers, reached an impressive 0.901. We also tested different fine-tuning strategies, such as training only the classification head and experimenting with various LoRA variants. The results of these tests are shown in the chart. Our method achieves SOTA performance using only the title and abstract. The table with the blue background shows how traditional algorithms perform in citation count prediction, with the best method barely achieving an NDCG score of 0.5. We also tested directly generating numeric values in string format, but the NDCG didn't exceed 0.7. As for fine-tuning with citation count or FWCI as the target, their performance was similarly underwhelming. There's a clear and significant performance gap between these approaches and our proposed method. We also conducted ablation experiments. Thanks to TNCSI-SP's time-resilient design, our method can better capture robust features from data across different years, resulting in superior performance. Some of you might wonder, what if the title and abstract don't provide enough information? Would adding extra data help? The answer is yes, but it depends on the context. We used GPT 3.5 for RAG to extract additional features from the full text and assess their impact. We found that almost all extra information contributed to reducing MAE, but not all of it was beneficial for improving NDCG. We also demonstrated a practical application of our method, predicting the impact of newly published journal articles. For this, we used the JCR classification system, an international standard. JCR divides all disciplines into 176 fields and ranks journals within each field by impact factor. The top 25% are classified as JCR Q1, the next 25-50% as Q2, and the bottom 25% as Q4. We applied our method to predict the impact of over 500 newly published journal articles from 2024 that were not included in the training or testing sets. The results showed a strong positive correlation between our predicted scores and the JCR quartile rankings. In other words, higher predicted scores aligned with higher JCR quartiles. This highlights the excellent generalization ability of our method on unseen data. Sharp-minded folks might already be thinking, could this method be used to optimize abstracts? And yes, that's absolutely possible. However, we strongly caution against making false claims about unachieved results or exaggerating the significance and importance of the method. The predicted metric is a probability output from a black box model inherently constrained by the distribution of historical data. The authors disclaim any responsibility for decisions made based on this metric. Thank you all. Feel free to reach out with any questions via GitHub issues or email.